Okay, I mentioned just now the Magnus effect, and I thought I'd better take a couple of moments just to tell you what it is, because it has an implication later on in the lecture. So the Magnus effect is, you've got to consider something circular. I mean, it could be a sphere, it could be a ball, but something that's round, and we place it in a flow. So let me do the sort of Bernoulli type flow pattern. So if the flow heads straight towards this circular object, it'll hit here, come to rest, stagnate, and we get our high pressure. These other flow lines are going to go around the outside of the circular object. And if you remember from earlier on, this is flow compression. It might be a little small for you to see. I've written it a little bit small. Flow compression. And where we squeeze the flow, remember what happened to the velocity? Velocity increases and pressure decreases. So in this region, where the flow goes around the side, we have all over really this area here, we have a lower pressure. Okay? There's a lower pressure around the sides of this circular object. And if we were to do the same here, we would get the same sort of thing. We'd get a low pressure just here. We'd also end up, because of this area of stagnation, with a high pressure. So now you can start to consider that high to low, there's a little bit of backwards drag, okay, that you can actually see the direction of high to low here. And what will happen in real life behind this object is that this will create a spinning, eddying, and chaotic wake behind it. If you imagine something spiraling around, like water going down a plug hole, the center of the vortex that's created is very fast. If I have high velocity, what's the pressure going to be like in your wake where all this spiraling is? You have a low pressure region back here as well. So you can see that all these things are pointing towards drag being created. But what I want to concentrate on is where the stagnation, the high pressure is, and where the low pressure is. Because what I'm going to do now is I'm going to work on this one, but I'm going to have the cylinder or the ball or the sphere or the round object rotating as well as the flow going over it. Now what you would see here is that this one normally hits straight on this stationary object and you get a high pressure here. What actually happens is that as the flow approaches a rotating surface like this, the surface is rough and drags the fluid around in the direction of rotation. So this one, if I went for the midpoint, instead of stopping, actually goes around. So do all those ones over the top. And even some of the one underneath might get dragged around with it. This one, which we're going to sketch here, might make it round the lower side. And what you end up with is the high pressure, which was directly in line with the flow, is now slightly to one side. But what you have in this region up here is more encouraged flow over the top, even more flow compression, and possibly even a lower pressure than you did in this case. And what this means is that instead of just drag being created, if you spin a circular object in a viscous flow, you actually distribute the pressures asymmetrically. And what you find is that now your high to low has a component in the direction of the rotation there. So here, not only is this being slowed down by drag, but it's also being pushed sideways because of the pressure distribution. There are some ships that have innovative sail systems that exploit this. We'll talk about those later. But this is also how David Beckham can kick and score a goal by making the ball curve around a line of defenders.